All right, so as my colleague, I think, motivated this morning, a lot of next generation and today's generation wireless communications systems utilize increasingly complex MIMO schemes. And today I want to talk about some of the test challenges in testing and prototyping next generation MIMO systems. And what I see as one of the largest test challenges is the problem of synchronization between RF vector signal generators and signal analyzers. So in this morning's talk, we're going to talk about first an overview of multi-channel applications, and I'll kind of explain the reason for phase-coherent vector signal generators and analyzers. We'll talk a little bit about MIMO, beamforming, direction finding, and with that backdrop, we'll dive into the problem of synchronization and address not only the best practices for synchronization, but also we'll talk about the metrics we use to prove to ourselves that our channels are actually synchronized. So that's sort of the approach. At the end, I'd like to get to an advanced application, which is an issue of synchronization between vector signal generators and vector signal analyzers. And that's the challenge of AM to AM and AM to PM measurements. So as you're all familiar, over the past 20 years, the digital communication systems we use have evolved. And there's really 5 or 6 main key evolutions that have happened over that time frame to increase data throughput. We start with simple modulation schemes. If you remember, GSM uses GMSK, a very simple modulation scheme. From 2G to 2.5G at edge, we added 8 PSK. With WCDMA, cellular communications added turbo coding to improve throughput through better data encoding. With WCDMA, we also saw an increase of bandwidth from 200 kilohertz to 3.84 megahertz. And of course, with WCDMA and now LTE, we see uses of technologies such as MIMO and carrier aggregation to increase throughput. MIMO is one of the most interesting of these because MIMO was the first time that we were able to surpass the theoretical data limits from Shannon's theorem. And I won't explain in depth spatial multiplexing, but the principle of MIMO is that on the transmit side, we can transmit unique data from each antenna, and through reconstructing the channel through signal processing, our receiver can receive each of the unique data bits on the transmit side. So we use this practice in HSPA+, in 802.11ac, 802.11n, and of course LTE and LTE Advanced. For those prototyping and testing MIMO systems, one of the largest challenges is to transmit or receive signals in a manner that is phase coherent. And phase coherent means that each of my vector channels of my vector signal analyzer are perfectly synchronized in both time and phase at the same frequency. As we've evolved over time, you can see kind of the increasing use of MIMO technology for cellular standards. So 802.11g introduced a 2x2 MIMO scheme back in 2005. And of course, we're all familiar with 802.11n, which introduced 4x4. That's expanded to 8x8 since then with AC. Of course, in the 3G and 4G side, we're going to 8x8 or 2x2 down to 8x4 and even 8x8. I expect this trend will continue. There is also the challenge of physical size of a mobile device versus the benefit of an increasingly complex MIMO scheme. The future, or 5G, will continue to use MIMO, and in fact, PXI Technology is being used to prototype the digital communication system in LabVIEW. And so this particular system that you see is an 8x8 MIMO testbed. So there's 8 phase-coherent transmitters, 8 phase-coherent receivers, and all of these are synchronized. And with this testbed, Dr. Fettweiss at TU Dresden is using LabVIEW to prototype the next DSP algorithms for 5G cellular technology. So MIMO is a well-understood reason for having phase-coherent measurements, but it's not the only one. Another one is direction finding. So you have a transmitter and 3 receivers, and if these receivers are phase-coherent, we can use the phase difference between them on a received signal to locate the direction of a transmitter. Another application is antenna diversity receivers. Antenna diversity receivers are a way to increase the aggregate signal-to-noise ratio of an off-the-air signal. There's several techniques to do this, one of which is to combine signals. So here you can see, suppose I have a receiver on this side of a vehicle, a receiver on this side of a vehicle, and I'm combining the signal power from each of those antennas and feeding that to my receiver. Well, if I'm in a condition where I have a deep fade in signal power, combining the signal power from each antenna allows me to increase my effective SNR. However, this is only possible if my receivers are phase coherent, and they can be synchronized in such a way that the phase difference between them is 0. So given this backdrop of why synchronization between multiple channels of a signal generator and analyzer are important, I thought we'd spend a little bit of time explaining how we measure whether or not 2 transmitters or 2 receivers are phase coherent in the first place. And so I'll first define phase coherence to make sure that we're all expecting the same thing. So the notion of phase coherent means that the recovered phase of 2 signals at the exact same frequency is 0. So the notion of phase coherent at different frequencies is sort of strange because antennas from MIMO systems are always at the same frequency. So what we're going to do is look at how we achieve phase coherence in PXI signal generators and analyzers. Now the way that we can visualize this is by looking at the time domain of IQ waveforms. So I want us to understand and remember the relationship between the frequency offset and the IQ samples in the time domain. So let's suppose I have a signal generator and it's generating a CW tone at frequency F1. And then I have a receiver or a vector signal analyzer at a frequency F1. Well, if my center frequency of my generator and my analyzer are the same, my IQ signals should look like DC. There should be no frequency content in my IQ. Frequency is 0 hertz, which is DC. So here's, for example, baseband I signal versus time. Q will have a similar representation. Of course, sorry, this is my baseband I and Q. Of course, I can, from I and Q, derive the phase. And as long as my generator and analyzer are synchronized, my phase should remain constant for the entire duration of time. Now I'll contrast that with a frequency offset. So in this situation, my generator is at frequency F1, my analyzer is at F1 plus some arbitrary frequency offset. So you can see my analyzer center frequency here, and my generator has a frequency offset. That frequency offset will show up at baseband as a sinusoid. So the precise frequency of my offset is actually the frequency of the sinusoid. So you can look at the I signal versus time. Now the reason why I've introduced that is because it's easier to visualize synchronization of baseband signals if there is a frequency offset between my generator and my analyzers. So before I explain how we synchronize, let's first talk about what not synchronized looks like. So in this case, I have a scenario where I have a vector signal generator. It's producing some sort of pulsed signal. You can see that it's pulsed because I have my I signal is nothing, 0, and then I see a sinusoid. In this particular case, you can see when my signal analyzer channels are not synchronized, I see two effects in the baseband. First, the start of each acquisition time is delayed. So in this particular case, there's roughly 200 microseconds delay between the start of each acquisition. Also, you can see that the phase of this sinusoid is different. The phase of the sinusoid is dictated by the start phase of my vector signal analyzer. So in this particular case, my phase is different. Moreover, if my local oscillators are not shared between each channel of my vector signal analyzers, this phase will change over a long period of time. So we'll contrast not synchronized with perfect synchronization. So now I've started the acquisition of each of my vector signal analyzers at the precise same time, and I've shared local oscillators between them and compensated for every phase offset. And so you can just barely see the red and the blue, but the signals are purely overlapping now that these signals are synchronized. So that's kind of a way to visualize synchronization in the time domain. To give this a quantitative metric, we can measure synchronization simply by extracting the phase of every IQ sample. So when our VSA downconverts samples to IQ, we can simply take the inverse tangent of Q over I, and that gives us an instantaneous phase per sample. So you can imagine generating a CW source and extracting arctan of Q over I, and you get phase sample by sample by sample. Now, the metric of synchronization we'll use is the difference in phase between channel 1 and channel 2. And so this delta phase on a sample by sample basis is the metric we're going to use to prove whether or not two channels are synchronized or not. Now the math, it's not quite complex. In LabVIEW, this is actually fairly simple. Here we take an array of complex samples, and I can simply pull out the phase from this LabVIEW primitive on a sample by sample basis. So I want to talk about two ways to represent a phase difference between two vector signal analyzers. So if I look at this vector or this phase difference on the Cartesian coordinates, I can see a phase and a magnitude of that difference. Now the thing I want to point out, in an ideal system, the phase difference between my two vector signal analyzers should be either constant or 0. Also, however, if my two vector signal analyzers are subject to phase noise that is independent of each other, you'll see the phase wander in this direction over time. And that's a classic view of phase noise in the Cartesian domain. Finally, if the number one contributor to phase difference is Gaussian noise, you'll see the phase of that signal blow up in a circle where the magnitude errors of I and Q are contributing to the phase error. So that's one way to visualize phase difference. Another way, and this is my preferred way of measuring phase difference, is to look at it on a histogram. So with a histogram, we take a large number of samples of phase difference, and we put them in bins, and we can see the statistical distribution of phase difference between two signal analyzers. The reason why I prefer this method is because we can use information about the shape of the difference to understand the primary source of phase error. In this particular case, we can also see not only the shape, but also the range. So you can see excellent synchronization, plus or minus 0.1, less than 0.1 degrees, and worse synchronization, plus or minus 1 degree. So now that we've talked about how to visually understand if two channels are synchronized, next I want to talk about the methods that we use to synchronization. And I'm going to compare those methods statistically to see which method is the best approach. So before I do that, I want to kind of explain my summary before I explain the results, because I think these will be more obvious as you see the results. The most important tenet is that the local oscillator is the single largest contributor to phase error. And so sharing the local oscillator between two signal generators and two signal analyzers is extremely important. Now we're going to contrast the LO, or local oscillator sharing, with sharing of merely a 10 megahertz reference. If we take two signal analyzers and we share a 10 megahertz reference between them, we can achieve what I would call pseudo-synchronization, where you might prevent long-term drift, but there's still a substantial amount of short-term drift. Also, we'll talk about cascading LOs. And then a final thing I think it's interesting to know is that with today's technology, we can accurately synchronize the phase of a signal generator with a signal analyzer. And the reason why this is important is because this allows us to perform much more advanced stimulus response measurements where we can effectively use our vector signal generators and analyzers almost like a network analyzer. And that's an extremely powerful technology. So to explain the hardware architecture of synchronization, I thought I'd give the background of what a synchronized 8x8 MIMO system would look like in PXI versus traditional instruments. So if one were to configure an 8x8 MIMO test system using traditional signal generators and analyzers, it takes up a lot of space. In PXI, much of the synchronization and trigger routing can be done on the backplane, and the modules fit nicely into two chassis. And these are physically the correct size. In fact, using PXI, we commonly produce 4x4, 8x8 MIMO test systems. In one chassis, you can fit a 5x5 system with 5 vector signal transceivers. However, we've also had customers daisy chain multiple PXI chassis. So you could easily go up to 16 by 16 or even 64 by 64. Now the typical configuration for that is someone prototyping a next generation communication system. And we've had several people do that. So on the synchronization side, I think the best way to understand how synchronization occurs is to look at the block diagram of a receiver. So this particular diagram shows the block diagram of a direct down conversion receiver. And we can see that using direct down conversion, we have a local oscillator that drives an in-phase and quadrilateral phase path at a 0 and 90 degree offset. That signal is filtered, digitized, and that becomes our I and Q signal. Now, to synchronize two channels using direct down conversion, the most critical element to share is the local oscillator, because that's going to determine the start phase and the continued phase of every acquisition. It's an easier task historically, but we also have to share the start time of each ADC as well as the sample clock of each ADC, because if those are not shared, we'll get some phase error as well. The physical way you would share the LO is with this local oscillator in and out port. those can be cascaded together so that multiple modules can accept an external local oscillator versus an internal one. Now, I want to show that diagram to contrast it with synchronization on a traditional vector signal analyzer. We saw the challenge of size on using traditional vector signal analyzers for synchronization. However, a secondary challenge is that traditionally you cannot get full phase coherence between rack and stack benchtop vector signal analyzers. Here's the architecture of a traditional spectrum analyzer. You can see this uses 3 mixing stages. Internally, that analyzer can accept a 10 megahertz clock, and it uses that 10 megahertz clock to drive each of the local oscillators at various mixing stages. What that means is that my best case for synchronization is to simply share a 10 megahertz clock between 2 vector signal analyzers. Doing so will give me pseudo-synchronization, but will not produce the full phase coherence. Over the next couple of minutes, we're going to share some data that illustrates the level of synchronization that can be achieved by sharing a 10 megahertz reference versus synchronization using the local oscillator directly. So I think the big question we'll ask and answer is whether or not sharing a 10 megahertz reference alone really makes a difference. Historically, everyone shared the 10 megahertz reference because that was all you could do. There wasn't an option to share a local oscillator. But what we're going to show is that sharing the local oscillator makes a tremendous difference in the actual coherence of 2 synchronized channels. So the first way we'll look at this is by looking at the phase on a sample-by-sample basis over a period of about 100 milliseconds. And what I'm showing is I have 1 signal generator connected to 2 signal analyzers, and I'm using one of 2 ways to synchronize those signal analyzers. In the first way, I share merely a 10 megahertz reference. And then I use the signal analyzers, and I take the IQ data from those, and I measure the phase of every sample, and I subtract the phase from each analyzer to get the phase difference. What we see is that over a period of 100 milliseconds, I'm seeing plus or minus half a degree in phase difference between my 2 signal analyzers when I only share the 10 megahertz reference. By contrast, when I share the local oscillator, my phase difference is much tighter. In fact, we'll show that this phase difference is actually driven by signal-to-noise ratio rather than any phase element of the signal analyzer. Now, we can also look at that using a histogram. And I think a histogram is useful because it shows us the distribution of phase. So you can see when I share a local oscillator, this appears to have a Gaussian distribution. When I share the 10 megahertz reference, and this is over a short window, I believe it's 100 milliseconds. Over the period of 100 milliseconds, I see what appears to be a Gaussian distribution when I share the local oscillator. However, what we're going to see is that over time, this range is going to increase, and the distribution is no longer going to be Gaussian. So, over the next few slides, I want to explain the impact of various environmental factors on synchronization. The first is phase noise. So, one of the best ways to assess the impact of phase noise on synchronization is to simply change the center frequency of my generators and analyzers. Because often what you'll see is that phase noise will degrade with frequency. It depends on the architecture, but with these particular conditions, I can have 3 data points of phase noise. Now, what this shows us is that in the case where the analyzers are only sharing a 10 megahertz reference, phase noise is the #1 contributor to the phase difference between 2 signal analyzers. What you see, this is a case where 2 signal analyzers are synchronized using only a 10 megahertz reference. And what you see is a nominal level of synchronization plus or minus half a degree. As my phase noise degrades, the phase noise each vector signal analyzer experiences is going to be different. And the lack of correlation between the phase noise is going to produce substantially larger errors as the phase noise of the instrument themselves degrades. Now, by contrast, if I share the local oscillator, the impact of phase noise on synchronization is negligible. And the reason for this is because every channel of my vector signal analyzer experiences the exact same phase noise. So when I subtract channel 1 from channel 2, and I have an impact of phase noise, that phase noise is affecting each channel in the exact same manner. And so what you see is, over a period of 100 milliseconds, the standard deviation in phase is almost identical. In fact, the reason why it's slightly worse at 6 gigahertz, I would believe, is actually due to a noise floor contribution that increased at 6 gigahertz over 1 gigahertz. Another way to prove to ourselves that in the case where the LO is shared, the noise of the instrument itself and the signal-to-noise ratio of that signal is one of the largest contributors to synchronization. One way to prove that is to configure my signal analyzer to have a variable bandwidth. So if I have a wide bandwidth, I'm going to allow a wide integrated noise to contribute to my measurement. If I use a narrow bandwidth, I'm effectively filtering out a lot of broadband noise. So in theory, if signal-to-noise ratio is my biggest contributor to uncertainty, I should get a measured tighter synchronization with a narrow bandwidth. Now, in a vector signal analyzer, the easiest way to filter is simply to lower the sample rate of my IQ acquisition. And so here you can see with a wide bandwidth, my standard deviation of phase is much higher, and with a narrower bandwidth, a smaller sample rate, the phase difference improves. So now that we've talked about the short-term difference in phase offset, I want to next talk about the long-term. Normally, long-term phase offset won't impact a MIMO measurement because a MIMO measurement on something like 802.11ac is equivalent for just a small burst. However, for applications like direction finding, you may be using or synchronizing those signal analyzers for a long period of time, and this can be an impact. So when we look at long-term phase difference, I'm going to use an 8 kilohertz bandwidth, and basically what I'm going to do is every 10 milliseconds, measure the average phase difference, and we'll track at 10 millisecond intervals the phase difference over a long period of time. Now, in the case where local oscillators are shared, you can see that over a longer period of time, I have more samples. So in a histogram, this peak gets taller and taller as time increases. I have more samples to put into my histogram. The other thing you observe is that the distribution over a short period of time and a long period of time is Gaussian. That tells us that whatever is contributing to phase error has a Gaussian distribution, and in other words, is really signal-to-noise ratio. Because this is a Gaussian distribution, the larger the number of samples, the greater my peak-to-peak offset is going to be. However, the larger number of samples is going to produce the same statistical standard deviation, and that's true with all Gaussian distributions. Now we're going to contrast this to the case where we share only a 10 megahertz reference. And what we observe is that over a long period of time, the distribution is no longer Gaussian. In fact, we get these dips and valleys. And what that means is, over long periods of time, changes in phase noise are usually driven by issues such as temperature, shock, vibration, and so the distribution is not uniform. In fact, just for the fun of it. We did this over a period of 5 days. And what we found is, while over a small interval, we can reasonably constrain the synchronization difference between two channels, over a long interval, like 5 days, the synchronization difference becomes very wide. So that gives us a little bit of insight into the impact of sharing the local oscillator between two channels of a vector signal analyzer. The same also applies to vector signal generators. And what this means for practical applications is that if you're testing a phase-coherent MIMO device with spatial multiplexing being used, if your analyzers aren't phase-coherent, that's going to contribute to a worse EVM measurement. And so I think this illustrates very well how the ideal architecture should be able to synchronize each of the channels on the generator or analyzer in a phase-coherent manner. Now, with that backdrop, I next want to go through one more application, which is the issue of synchronizing the phase of both the generator and the analyzer. Now, one of the reasons why this is useful is for more advanced stimulus response measurements like AM to AM and AM to PM, and I'm going to explain what those do. So let's imagine, for example, we have a vector signal generator and a vector signal analyzer that are synchronized. Now, these instruments can be synchronized when our vector signal analyzer is using direct down conversion. Traditionally, vector signal analyzers use a heterodyne or IF down conversion. What that means is that my local oscillator and my center frequency are different. However, if I use direct down conversion, that means my generator and analyzer can share a local oscillator at the same frequency. So before we talk about the measurement results, I want to first talk about a review of AM to AM and AM to PM. Many of you have probably seen this graph, which is kind of referred to as the compression point graph of a power amplifier. What it shows us is that the output power as a function of input power is not perfectly linear. As we're driving our amplifier into compression or into saturation, we see this curve in the response of our amplifier where we no longer have a one-to-one relationship between input and output power. So this is our theoretical response, and this is our actual response. Historically, the way that you would measure this is with a network analyzer, where you sweep the power level of the network analyzer and look at the received power on the receiver. However, when measured with a network analyzer, we're only measuring that with continuous wave signals. What I want to next introduce is a way to measure this with modulated signals to capture the memory effects of the power amplifier. So to measure this with modulated signals, you can think about it, the input as a waveform, think of the output as a waveform, and imagine comparing the phase and magnitude of every input sample with every output sample. If my signal generator producing the input sample and my signal analyzer, which acquires the output sample, if those are synchronized, then I can compare the phase and magnitude of every input sample with an output sample to get this AM to AM response. So here's an example of the input waveform in blue, right? So here's my input waveform. This is power versus time of a modulated signal. So here I'm looking at only the magnitude, and I'm scaling it in dB. In an ideal world, I would get this output in black, where the input and the output have the exact power versus time profile, but one is amplified per the gain. The reality is my amplifier has a saturation point, and as the output would theoretically increase beyond the saturation point, I get this compressed output. So with that backdrop, we can look at the configuration of measuring AM to AM or AM to PM with synchronized vector signal generators and analyzers. So I've broken this into two boxes, but on the vector signal transceiver, these are actually part of the same instrument, just different connections. So you can see on the transmit side, we're using direct up conversion. So I and Q directly up converted to RF. On the receive, RF directly converted to I and Q. What that means is that when set at the same center frequency, my generator and analyzer can share a local oscillator. And that will allow me to fully synchronize my generator with my analyzer. So when we measure AM to AM and AM to PM, we can think of taking every output sample and looking at the phase and magnitude versus every input sample. And what we observe is that if we look at the magnitude of those samples and we compare the input waveform and the output waveform, we see this gradual roll-off as my amplifier gets driven into compression. If we look at the phase difference between every input sample and every output sample as a function of input power, we see at the low end, my phase difference is dominated by noise. But as I go higher in power, you can see the gain expansion and then the hook in phase that happens when an amplifier is driven into compression. So this is considered the AM to AM graph and the AM to PM graph. And of course, we can look at gain as a function of power. And of course, as we're driving our amplifier into compression, it's no longer producing the nominal gain. Now, in order to make use of this data, we commonly will apply a curve fit to the extracted data. And what that does is it allows us to use this data set as a lookup table for something like digital predistortion. In fact, if I can extract this curve as a fitted graph, I can use the inverse of this curve to modify my IQ samples for the purposes of digital predistortion. And so that's one of the ways that AM to AM or AM to PM data are used in practical applications. The other interesting thing is that because I extracted that with modulated signals, I can assess whether or not there are any real memory effects of my amplifier. Now, given that application, I wanted to finally investigate the effect of synchronization on performing AM to AM on AM to PM. And so here's a case where I have perfect synchronization. And then here are some cases where I've offset my generator and analyzer by one sample at 160 megasamples per second. So you can divide 1 by 160 megasamples to figure out what that time is. And then 5 samples. And what you observe is that the accuracy of AM to AM and AM to PM is very dependent on the synchronization between your generator and your analyzer. And so this is a case where sharing the local oscillator is immensely important to achieve a proper measurement result. So in summary, many applications required synchronized multi-channel vector signal generators and analyzers. We saw this to be true with MIMO tests. It's also true with direction-finding and beamforming. And of course, synchronization between a generator and analyzer is important for AM to AM and AM to PM. Also, a modular platform for instrumentation is really the ideal platform to produce phase-coherent generators and analyzers. Not only can I expand to add more channels later on, but the ability to share signals like the local oscillator externally allow me to get the best level and the tightest level of synchronization. And then finally, with the VST, being able to synchronize the generator and analyzer allows us to do advanced stimulus response measurements such as AM to AM and AM to PM. So that gives you a little bit of context into why synchronization is important in MIMO, beamforming, direction-finding applications. So I want to thank you for having me, and I believe it's time to eat lunch.